Thank you. Thank you very much for the introduction. I also welcome everyone to my talk. It's a pleasure to be here and present you the results of our work that we did with our client. The work over building a system that applied complex event processing on massive streams of user interactions inside the client network. I'm going to share in the first part how we built the system, leveraging Flink and other technologies. And then later I will share some lessons we learned from running the systems 3 years in production. I hope that everyone finds it useful, interesting. My name is Krzysztof Zarycki. I'm an engineer and geek at heart, focused on big data from numbers of years now, working with Flink since I think it was Stratosphere, quite long. And I'm also a CTO and a co-founder of a company called Getting Data. Getting Data is a company where we create and help other companies build data-driven and machine learning-driven products, analytics solutions. We learned the craft at companies like Spotify, IBM, Netezza, and we focus on big data, mostly on it, where we gained lots of production experience over the years, and especially applying technologies like Flink, which we are happy to contribute back to. The client which asked us for help is Kcell, right? It is one of the largest GSM operators in Kazakhstan with over 10 million of subscribers. It has a strong development team, has a strong development background, which made very good environment for us to build solutions using open source technologies like Flink. And it's not only telco now, it has many other services that are based on data and analytics, which use a lot of data, I would say. Basically, what we were asked to is to build with Kcell a system that can ingest and process and make actions on many of the events, massive streams of events happening in their network and in real time, but not process not single events, but it should allow to apply custom logic to detect interesting complex events, right? And that, of course, that are pattern that we need to match or make aggregates of physical events and decide where to deliver the action to trigger some action in external systems. But what for? Let me introduce some use cases for such a system. In one of the use cases, we would like to detect a user that has prepaid card, and he tops it up very. Okay, I don't know where I was dropped off, but let's say that I will introduce the use case again. Okay, so one of the use cases where we would like to detect users of prepaid card users, subscribers, that tops up very frequently and uses their balance quickly. This can be expensive without any tariff, right? And it is inconvenient for them to top up all the time. So we would like to trigger a suggestion for them to enable a tariff which is less expensive and automatic. They don't have to top up. And what's important, we would like to do it while they still have a phone in hand, I would say, and metaphorically, of course, at least still remember the effort that they did. So we would like to do it in real time, as quickly as possible when we detect such a situation. On the right-hand side, we display a form of starting such a role in our system. What's important to note here is that we need to look at the aggregation period of multiple days, like 7 days. So the system that we are building must be stateful to support use cases like this one. Getting quicker through other use cases, like we'd like to detect users that are going into roaming to a particular country and using particular network, and spend in this roaming for several days. We would like to detect frauds, different case of frauds in roaming, or just other complicated cases that require complex event processing. And also, we'd like to automate the business in multiple occasions, like automatic SIM card activation, where a user just puts in SIM card into his phone and automatically is registered in the network. That's something in Kazakhstan that was not possible for a long time, but now Kcell was first on the market to deliver such a function. And Other stuff like dealer motivation, where we detect a purchase by subscriber that is attributable to a specific dealer, and we provide bonuses for him. And we do it real time, which is very important here, which makes a gamification out of it. So it's an instant gratification for performance of the dealer. We would like to inform users that they are using roaming extensively, which brings loyalty, reduces churn. Or we would like to trigger, deliver some knowledge to third parties, some insights. For example, that a user goes to a shopping mall and we can send him an offer that is localized to that shopping mall. So generally, we have, I think now like 15 cases originally it was around 15 cases. Now it was 2 times more. But out of that, we run around hundreds of rules in production, because each of these use cases can actually be run in multiple configurations. So the scale is large. It's scale in number of use cases, but also in number of events that we need to process. So we started from 150, 160,000 of events per second, but we grew now into 2020 to 500,000 events per second, which sum up even to 1 terabyte of data per day. Let me start with the overview of a solution architecture. We divide the system into several layers. One is like ingestion that focuses only on pulling data out from multiple systems, putting that into an events hub as a stream, and which waits for consumption. And then we implement business logic in the events processing layer, those triggers. And finally, there's a ingestion layer that pushes the results out to multiple systems that wait for the triggers, the actions, the notifications, like marketing platform or fraud detection systems. To deliver this architecture, we use several open source technologies. We used NiFi for the ingestion and outgestion, Kafka for Events Hub, and Flink, of course, for implementing the events processing. Of course, there are a few things in the back. There are systems that enable operations, logs collection, metrics collection. There's also a system that allows users, Kcell internal users, to define the triggers, run them, and control them. And also there is a strong push on security to provide authentication authorization. In companies like Kcell, it is a must to provide that. Finally, the system fits into the larger picture that supports other use cases than pure stream processing. The system feeds data lake that we built using Hadoop technologies. By the way, we are on premises. We are not in cloud. So we need to build our own system for all of those components. And so the data lake stores history, of course, of all incoming events, brings analytics with use of Hive, Spark, and others. We also develop specialized services that support interactive BI. On top of that, business monitoring and dashboarding, and also we built a whole stack of technologies to apply ML, machine learning opportunities, on the large scale. Right, we want to scale out machine learning to get from experiments to production in minimized time, and to commoditize, I would say, machine learning across Kcell. So as you see, there is a larger picture, of course, but let's get back to stream processing and zoom in a bit. It's worth sharing that our ingestion pipeline are done all in streaming, right? Even sources like FTP are being converted to streams. And there are few simpler jobs that do transformations, prepare the stream, convert from CSV to Avro, etc., etc. And finally, there is this central trigger job that produces out of multiple streams notifications that are delivered by NiFi to other consumers of that. I'll skip that comment. Let me describe the crucial design that we had to apply here to implement here. But first, let me highlight the problem. So as I said, we will have not one configuration of a use case, but many. And that makes up to even hundreds of configurations running at once. Typically, a solution would be to have a job like a SQL query per such rule, but it won't work in our case. We would need to pull data from Kafka, deserialize the objects, and probably sort by time even hundreds of times. Of course, each of those jobs will will also consume resources and for job manager, task manager overhead. That would be extremely inefficient. Not to mention that each role would actually require deployment of the job to the cluster, which takes time and keeps a separate checkpoint, by the way, which also needs to be managed. So we implemented an approach already known in Flink community. That is, we have a single job that runs all the triggers. Triggers are just code branches in a single job done in Java. And the job interprets commands as an external stream of commands that start or stop all start triggers. And we managed to do it this way. We managed to run very efficiently over hundreds of rules in a single system, because the price of pulling data in and managing the jobs was shared. So let me give you a simplified peek into how the function look. We have a Flink job that shuffles the incoming events by user ID and then applies a keyed coprocess function on top of it. The one stream that it accepts, of course, is data, right? All the events from the network, and another stream that this coprocess function accepts is the command topic, the stream of commands. This coprocess function has inside an internal pipeline that first sorts sort the events by time, because trigger rules cannot work without cannot work with out of order data. There are possibly some pattern matching functions that needs data sorted, and events are deduplicated for correctness and then routed to multiple triggers interested in some specific event types. There's also a nice thing about having all the triggers in a single job, that is that we have shared memory, so the state can be shared as well. So you see here also a state updater entity that creates a state common for all the triggers, where we store some generally useful user features. For example, a balance on a prepaid card that is used by multiple triggers. So what do we gain by this design? The most importantly is that we share and therefore efficiently use resources, right? We also share work because we pull from Kafka once. We deserialize once, interpret data once, and then deliver that to many triggers. We also gain the possibility to share the state, as I mentioned. And finally, users of the system don't need to wait for a deployment of a new role, and they don't need to ask IT, right? IT does not need to be involved. But this design comes with some cost. The biggest of it is that whenever there is a failure or misbehavior, it affects actually the job, which affects all the triggers. There is no isolation out of the box of the triggers or watermarks or exception handling or class loaders. So it is also trickier to debug because code is shared, because one job runs multiple branches, does many things. And also the code paths are externally enabled. So it's harder to reason about the system. And last but not least, there is no way to use goodies like higher level Flink APIs. No way to use SQL, no use the table API or set library to implement triggers. At least not out of the box. Okay, maybe I will have time to talk about it. Summing up how we build the system, because I will then go to lessons learned. We built a whole, I would say, interdisciplinary team that contained people from our company and client company that was strong programming team, and we applied strong, I would say, rules about testing, about code review, code quality, and also knowledge sharing. Because as we work as one team, the knowledge has been shared consistently and continuously, I would say. We also applied agile practices to our work. And with this approach, and with also strong DevOps and DataOps actually practices, we were able to deliver this system very quickly. We were live even in less than 4 months with a first production use case, running 24/7. So, and of course, there was continued development further on, but first use cases were very quickly live. We are all together very proud of this. Business feedback was very great, right? The project is considered very successful by the client. The ROI for the project was enormous. It brought value from marketing, from fraud detection or churn prevention, and it actually returned in less than a year. And the good feedback is that we do get complaints when the system is not working. So that means some people are actually using it. It is indeed useful. And the client team has many new use cases planned and monetization ideas for it. And what's also great, and we are proud of it, is that the client team can develop the system themselves without actually our help, which means knowledge sharing worked very well. Okay, to save time because of these technical issues, I will go to the lessons learned. Let me jump to directly to, I mean, we would like to share some lessons that we would like to know before we started, so I hope that you will find them useful. Let me start with a general remark. The fact that was imminent in this project and many other projects in our past is that we think that the solution to the problem at hand is mostly in a business logic, right? The problem at hand is with business logic. We think about how we can solve it with Flink. We used to focus on it. We believe that this is the clue, the hardest part. We tend to diminish the importance of other aspects like engineering, very good engineering, thinking of a larger system, how it fits, where the app is going to be introduced, what infrastructure, how to feed the application with stable data flow, or how we are going to consume the results and how we're going to interpret them, how we are going to explain them. These kind of things are usually diminished compared to business logic. But the reality is different, right? The business logic, while still it's considerable, it's a piece inside in all this puzzle that all the components should work together, right, to create a sound end-to-end systems. We have seen this multiple times in our journey, and we advise to always consider in planning that that business logic is just one of the pieces of the whole bigger picture. Now, I would like to talk about some Flink stories that are at heart. Some are focused on the approach that we took, which is the single job for multiple triggers, like this lesson learned. With growing number of trigger types and instances, we quickly realized that single job, running all of them, is a bad idea. Some of the reasons are that sources have different pace. Some were more unordered, some were less unordered, had low latency. And the trigger job was as slow as the slowest of the sources. And so it didn't fulfill requirements for some of the triggers. So the improvement we did was to split this job into many, where each runs a group of triggers, those rules. Thankfully, we were able to do it because triggers rarely consumed more than one source, like a slow and fast. If it was a case, this approach would not work. So we used the simple idea to split more experimental triggers, less importance from the critical ones that needs to run 24/7. This design idea does not come without a cost, though. All right, as you know, having multiple jobs to deploy, operate, and monitor brings some cost. Next lesson is around performance, right? During our work, we used a very simple approach that we took all the raw events, converted to Avro, and pushed it to the triggers as quickly as we can to apply triggers on top of it. But then these events were landing going through the system very fat. I would say they were shuffled fat, and then it buffered fat, I would say, which means they had a lot of fields that were unnecessary for triggers themselves. So we looked into the triggers, and we see that only few fields are actually used, few event types are used, and we decided to introduce an operator which limited the number of fields, limited the event types quickly before actually the shuffling, just after the Kafka consumption. It also optimized some data representation, like going from string IP representation to byte representation, and that gave a significant boost. That was one of the largest boosts that they have seen, and of course lowered the memory use as well in buffers. But the drawback is that it required manual coding of that component that has to be maintained in the pipeline when someone introduces a trigger. But we advise to apply such a technique in your cases if you have something similar. Next lesson will be about pipelining of the jobs. This pattern is very tempting to implement in a stream world, right? Where you split multiple processing steps into multiple jobs with Kafka as a buffer in between. It's a similar approach to how you split a bigger system into microservices instead of implementing monolith, I would say. But my advice would be to think twice before you actually do it. Why? Before it brings a whole a whole world of pains, I would say, to your pipeline. You end up with multiple jobs that create unrelated checkpoints, and the biggest disadvantage of it is when you would like to rewind processing. And we needed rewinding processing several times because of the bugs in the upstream steps. And when you have such a bug, you want to rewind the upstream step, then you actually produce duplicates to the step 2, the downstream step. So as the step 2 is actually stateful, it actually influences the results because it sees the duplicates. It's not easy to remove the duplicates. So you actually need to rewind the step 2 as well. But it's impossible to rewind them to the same offset, I would say, synchronously, because the checkpoints are unrelated. And actually, offsets in the Kafka are also unrelated because they come from different topics. So it is a very hard problem, the rewinding, when you have a pipeline of multiple jobs. And one also big problem that comes from this design that hit us was that data easily became unordered. Why? Because step 1 can shuffle the incoming records before they get to the step 2, which is the downstream step. I could explain it more, but to make it shorter, imagine that you have an unequal number of partitions, number of sources, the Flink parallelism and final partitions, the output partitions of your job. That is, you would think, embarrassingly parallel. And when there are some problems with Kafka partitions on the beginning, for example, the data from that partition is late, it gets written in a mixed order at the end. So if you're doing this approach, you're doing the multiple steps approach in the pipeline, make sure that you make the number of input partitions and output partitions equal to Flink parallelism. There is also things about using the right partitioner in Flink, but you can get that easily in documentation. Then it's fine when partition is down, your output partition is down as well for this period, but the data does not get mixed. Okay, next thing about testing, the lesson learned here. We have a pre-prod environment where we tested a lot our application, but it always was a pain because the pre-prod was not in sync because it had some problems. And actually, a lot of bugs did not occur in pre-prod that have occurred in production. So our solution to this was to bring in incubating mode, something we call incubating mode. So we fork we create a second job that is a mirror of the main production job that starts from the same save point and runs on production data, production input, but just creates a separate output, right? That is that goes to trash, and only developer looks into it to interpret results. That was a great idea. It works very well. It found a lot of bugs that occurred only in production environment. So I advise you to do something similar in your development. There are future ideas to extend this, like making this incubating mode actually a blue-green deployment, or even running both jobs together and do A/B testing, so both jobs actually produce production results. But there are tricky things around in taking the output from those two jobs when your job is stateful. I'm not going deep into that, but I just say it's definitely not so easy to just, like in microservices world, do gradual deployment or A/B testing of the Flink jobs, stateful Flink jobs. Okay, next lesson that we learned, the timeouts. The checkpoint timeouts is a ticking bomb, as we say. When for whatever reason the job slows down somewhere in the middle, and that was like the most common reason, like when we have a problem to write into Kafka, then we got a lot of exceptions and crashes of the Flink job because the checkpoint did not finish in the reasonable time. And it was because of Kafka could not keep up, for example, right? Or could not, or had some problem with the broker. Or actually, also we had a problem with unordered input that made it, this situation, it caused the situation. So checkpoint timeout, we definitely had this problem a lot. But what were our solution to that? First approach was to put quotas on Kafka consumption. And by the way, we worked with Flink for, the problem occurred already a year or 2 years ago. And the only solution at hand we had was to put quotas on Kafka consumption. So we actually configured Kafka not to produce to block the consumer, I would say, to slow down the consumer. But the solution now, which we would apply, getting back to the latest point, would be unlight checkpoints. We didn't have a chance to do it, but we believe that this could be a solution for the problem. So definitely look into that if you experience checkpoint timeouts. Getting to different component now, NiFi for a second. I know that NiFi is not a part of this conference, but generally a lot of people use NiFi, so we hope you will find that useful. NiFi has a problem that easily reorders data, where, as I mentioned, order is very important for our system. So whenever there is a problem with NiFi, when it writes to Kafka, it rejects the flow file, it goes to a failure relationship. We in our flow, we do a retry of that flow file, but then data coming in a normal flow is being mixed with those flow files that are retried. So the data is written to Kafka unordered, and that's only in a single NiFi. You usually create a cluster of multiple NiFis, and other NiFis are working fine, so they are writing to the same partitions, actually, other data. So the data very easily get mixed. The other problem that we mostly see with NiFi is the limited high availability, where if one NiFi fails, it actually locks in the data that it pulled in because it has internal buffers, and it's unavailable until you wake it up, I would say. I will limit on that. There are also other problems with NiFi, like CI/CD missing. There is NiFi registry, we do use it, but it's still hard to implement correct CI/CD with it. The solution that we want to apply, we haven't yet, is to recode some pipelines with Flink. Actually, we see that Flink could be a better idea for linear pipelines of pulling data in and just putting in Kafka. There are other solutions that we apply in different client contexts, but I'll need to skip that. Now getting to observability or operations in general. Flink fails. Flink definitely fails often and early. We encounter that, and we need to protect for that. Of course, we run in Yarn because we are coming from Hadoop world, and Yarn restart strategy that just kicks in, right? It does not solve, although it does not solve all the cases. Some cases are unrecoverable. We claimed the reasons, but we are not sure of them. So after 10 restarts, for example, of Yarn, the job still does not wake up. So we cover such cases with a simple solution that we have some application that ensures every 5 minutes that the production jobs are actually running. And that suffices. That's really a good solution. We use Rundeck to do it. So we advise you to also think about such a solution that makes sure that applications are running continuously in production, even if you're using Yarn. Another thing is the monitoring, right? Big data requires big monitoring. And in our case, we have tons of tons of events. The jobs produce a lot of events, a lot of metrics. And InfluxDB that we used in the beginning did not keep up. We changed to Prometheus. That was a game changer. And I must say that we are very happy of using it. The problem is with service discovery on Yarn, but you can manage to overcome it with custom scripts. I'll finish on that. The same with logs. We used Elasticsearch for a long time, but then we experimented with Loki, and we are very happy of it. I also advise to look at Grafana Loki. One of the biggest advantage of it is that logs and metrics land in the same interface, Grafana, and so you can correlate them easily. Another big thing, we got a request from our client that we want to know why such a trigger launched or did not launch when I expected it to launch. The users of this, internal users from Kcell, wanted us to explain, but we could not. To do it properly, we needed to trace all the decisions of the system. But there are multiple decisions, multiple steps of processing each event, and that produces multiplication of the traces, right, when we implemented it. So in our case, it was several millions of traces actually per second. It is very hard to actually crunch this data. So we finish on landing this data on HDFS, but we are thinking how to actually process it. Still experimental work. And if you have any advice on how to solve this case, I'll be very happy to speak about it. But generally, this explainability problem occurs here. Okay, I'll finish on that, on the lessons. There is one thing that I maybe want to mention here before we end up, is that we are fighting for having DSL for the roles, for the trigger roles that the user define. We would love to have SQL for that, but it's currently impossible to implement, of course, with SQL. We are doing experiments inside of our company that will enable that to use SQL, I would say, in a dynamic way. But I hope that we'll have a possibility to share something about it in the next Flink Forward. I will finish on that to give you a chance to have questions.